Hello, my name is Jed Murdoch and welcome to Module 4 on Metapopulation Dynamics. In this module, we'll cover the basic concept, the idea of metapopulations, what a metapopulation is, what the dynamics of metapopulations are, and why that might be important for managing some species, especially those that might exist in discrete patches across a landscape. So let's begin. As population managers, as wildlife managers, conservation biologists, for example, we are oftentimes concerned with the conservation of a particular species. That might be cougars out in California or salamanders in Vermont. And we spend a lot of time and energy trying to understand characteristics of populations in order to inform our management decisions. So we might be interested in quantifying those things that govern the way populations work, like birth rates and death rates. We might also be concerned with how humans influence the species, how they may alter the landscape, they may alter habitats, for example, that have some influence on the dynamics of that population. But what we see, especially in this modern world, is that species oftentimes don't exist continuously across the landscape. And in many cases, we have species like cougars and salamanders as well occurring in fairly fragmented, discrete patches in a landscape or in particular ecosystems. So we have this non-continuity, and that creates some management challenges. So consider a case involving a tiger, right? We know tigers are very charismatic species. We know that they exist in very small, isolated populations. If we think about them in the Terra Arc landscape of Nepal, the foothills of Nepal, right, as you can imagine, tigers once ranged throughout that foothill region, that Terra Arc region, pretty continuously, but now they're isolated in fairly discrete areas of suitable habitat, surrounded by a matrix of relatively unsuitable habitat. There are a lot of people there's a lot of development and so forth. So we are interested as managers oftentimes in trying to protect or prevent the extinction of that whole population. And that's where really the metapopulation idea comes into play. What the heck is a metapopulation? It's sort of a fancy term. What it really perhaps means is simply a population of populations, right? So a big population that's made up of a whole series of other smaller populations. And we oftentimes refer to those smaller populations as either sites or patches, or usually subpopulations. So if our tigers are behaving like a metapopulation, if indeed we have a population of populations, meaning not only do we have these various subpopulations, but they're connected in some fashion through either dispersal or immigration, so some connection between them. If indeed that is the case, then we may sort of broaden our lens on how we approach management of that species and work to ensure the persistence of that whole regional collection of subpopulations, as opposed to putting a lot of time and energy in trying to prevent extinction of some of those smaller populations. So to demonstrate this point perhaps a little bit better, let's consider another example, one that may be a little less charismatic, but one that I think is very effective, and that would be the case of the marmot, the Siberian marmot. The Siberian marmot is a large rodent. So this is a big guy, maybe 6 to 9 kilos, good-sized rodent, and they live in the steppes of northern Asia, so throughout Mongolia, parts of China, parts of Russia as well. What do we know about marmots? Well, these marmots live in colonies. So they're organized in these kind of extended social groups around colonies that might cover several hectares. And these colonies have large burrows, so they spend a lot of time in these subterranean burrows, and they come out during twilight hours, during crepuscular periods, to carry out most of their normal activities. So as you can imagine across this landscape, we have in, let's say, the middle of Mongolia, a series of colonies, which we might call subpopulations. And they interact to some extent because there is some migration, some dispersal, some immigration that occurs between them. But what we see among this whole collection of colonies, or perhaps subpopulations again, is that they sort of wink in and wink out over time. And what do I mean by that? Essentially, we have some populations that just go extinct. They wink out, they disappear. And then at the same time, we see occasionally these particular colonies, these sites, winking in. So they become colonized at some point. So as you can imagine, right, again, all of these different colonies kind of winking in and winking out over time, sort of like light bulbs going on and off. So let's consider a population of marmots. Let's think about what that probability of going extinct might be as a starting point. So the probability of extinction might inform how we describe this system, right? So the probability of extinction, which we might call PE, probability of extinction, is a value that would range from 0 to 1. So if the probability of extinction is 0, what would that mean? There is no chance of extinction. So all of those colonies, which might be several hundred, for example, will not go extinct. So if we had a value of 1, if the probability of extinction was 1, we have the opposite case. So in that case, every single colony will eventually go extinct. So the range here is from 0 to 1. And let's say we studied this population over the course of 1 year. So let's start by looking at a single colony of marmots, and we'll try to estimate what the probability of persistence is, or the probability that that colony will be around for some time. So we've got our marmots here, we've got a single colony, and in our first year we may have estimated, based on perhaps studies of watching marmots and their behavior, we might have determined that the probability of extinction of a colony, any colony that might be out there, is 0.7. In other words, there's a 70% chance that that colony will go extinct. So our probability of extinction is 70%. What then is the probability of persistence? For our single marmot colony system, the probability of persistence is 1 minus the probability of extinction. Easy enough, right? So that's 0.3 or 30%. So within our first year, let's say, if that's our time frame, there's a 30% chance that our marmot colony will persist in the landscape. How about 2 years now? So after 2 years, what would that probability be like, given that we know there's a 70% chance of extinction for that particular colony? So the probability in our second year, the 2 here just indicates our second year, so the probability after our second year, is simply the product of our probability of persistence in the first year times the probability of persistence in the second year. And we know that's 0.3 or 30% in the first year and 0.3 or 30% in the second year. So we multiply those two things together, and what do we get? We actually get 0.09, which is basically 9%. There's a 9% chance after 2 years that this colony will be around. Those aren't very good odds, really, to be honest with you. So we can take this equation now and we can generalize it a little bit more. So we do that with this equation here, and that's just simply Pn, and n here refers to our number of time periods. That would then equal the probability of persistence raised to that power. Okay? Easy enough? Let's now consider a situation in which we have multiple colonies. So now we're not simply looking at the behavior of a single colony, But let's say we're interested in a small metapopulation, so a system in which we've got multiple colonies, multiple sites out there, and let's say we're going to keep it simple. Let's just say we're dealing with a situation in which there's 2 colonies. In this case, we have, again, the same probability of extinction. So each site stands a 70% chance of going extinct. There's a 70% chance that each one of those sites will go extinct, and that's constant. So that's something that we know about marmot colony sites, let's say. So the question is, given that we've got 2 colonies in this value, what do we expect the regional persistence to be within our first year? And so that would be 1 minus the probability of extinction of our first colony times the probability of extinction of our second colony, and we know that that's what? That's 0.7, and we know that this is 0.7. So what does that give us? 0.7 times 0.7 is 0.49, and 1 minus that should be 0.51. In other words, there's a 51% chance, now that we have 2 colonies, that it will persist in that year. And that's a little bit better than our previous example in which we have a single colony. It had a 30% chance of persistence. So just having this extra colony in our system really increases the persistence, the regional persistence of our what we might call metapopulation. So we can now generalize our equation a bit more, and we can say the probability of x, and x here is the number of colonies, is simply 1 minus the probability of extinction, right, which we know is 0.7 in this case, raised to the x power. Okay, so if we have a situation in which we have 10 colonies, then what's the probability of persistence, of regional persistence? What's the chance that at least one of those colonies is going to be around? And so we just use this generalized equation. We now have 1 minus 0.7 raised now to the 10th power. And if you're really good at math, you'll probably come up with that answer quite quickly, but it ends up being, if I've done my own math correctly, 0.97. What does this mean? It means there's a 97% chance that at least one of those populations will persist, even though it's likely that any one of those colonies will go extinct, right? The PE was 0.7 or 70%. I think an important point here that helps underpin the metapopulation concept and idea is that multiple colonies, multiple sites spreads out this risk of extinction, which means that it perhaps is more valuable to focus on ensuring that we have regional persistence as opposed to local persistence. So if you have limited resources, we may be better served by investing those resources in ensuring regional persistence instead of putting all of our eggs into a basket to protect one individual population.